Hello fellow problem solvers. So they're going to be doing a problem from the ELMO 2017, problem number 2. I suggest you try this lovely geometry problem out for a minimum of 15 minutes, ideally 45 to an hour, not more than 2.5 hours. If you'd like to go along with us, draw a diagram and put your first ideas out on paper for the next 10 minutes. So now, without further ado, let's begin. I remember trying to solve this problem back when I was preparing for my 2017 and final IMO, and I loved the solution. ELMO is one of my favorite competitions because they usually had, at least when I was competing, amazing problems. Like ones that I truly love. And this one is, it seems it's a problem too. So it's a medium difficulty problem. If a medium difficulty where medium is defined as IMO level medium. And here, it's actually very interesting. So we have, just if you look at the problem, so we have a triangle and we're going to need a circumcircle. So we're going to have a circumcircle as the center. We're going to have an orthocenter H. Let's have H. The way I draw usually H, if it's something that's in a problem that's symmetrical with respect to B and C, but then I need AH, I'll usually reflect. I'll draw it to the circumcircle and then reflect. In my mind, I will reflect it here, and then I'll know, okay, that's where H is. And now we have perpendicular here, and we have this circumcircle. We have M, we have B, C, A, and really PQ is you take from M any sort of line. Let me use another color for that line. You take any sort of line intersected at points P and Q, and we must prove that the orthocenter of the triangle APQ lies on the circumcircle around ABC. And this is not simple, right? This isn't easy. So let me see if I use maybe green instead of yellow. So the orthocenter around APQ. How do I ever get to that? So for me, after I draw the diagram, I go, okay, I know, for example, that MH in this intersection, call it Q, I know these are collinear. Actually, let's call it R. I know these are collinear. So, and I know that this angle right here is 90 because when I reflect HM, H with respect to M, I'll get this is on the circle, and I'll get that this angle here is 90 because BH is parallel to this H prime C, and BH is perpendicular to AC, so H prime C is also perpendicular, so this is 90, and then this is 90, and then this is 90 as well. That's the proof of the lemma. And here, I'm thinking, okay, the orthocenter here is at R, because it's a 90-degree triangle. So it's not super duper useful now. And I was thinking, okay, as I draw different P and Q, say call this P prime, this Q prime, as this is moving, where is the orthocenter going to be? For example, in this triangle, APQ, the orthocenter is going to be on this side right here. And the question is, how can I find some relationship between these P and Q? Why? There's a lot of questions that come to mind here. For example, why from M? Why is M so special here? Right? Because it's not, if you do it from B and C, this is not going to hold true. If you do it from, I think, any point that's not on this line, it's not going to hold true. Because it has to, RH, if you're going to have another point here, no, actually, I think this is the only point where this is true. I might be wrong. But why is M so special? Why can we use that's true about M and this circle? Right, so for me, I want to now, okay, maybe look at this B1 and C1, the theta perpendiculars. What do we know about M? Here's where I invite you to pause for 10 to 15 minutes, try to push the problem further. And here's what we know about M. We know, for example, that this thing right here, MB1 and MC1, are tangents. So maybe there's something there. We know that MB1 is MC1 is MB is MC. And we have this sort of maybe power of point. Is it useful? We don't really know, is the thing. I don't know if it's useful or not. Maybe it is, maybe it's not. In fact, I've actually forgotten how this problem goes, so I might need to pause at some point in the video and try to figure out a solution of my own. So we know MP times MQ is going to be MB squared is going to be MC squared is MB1 squared. Now, another way to look at this is there's this line here from M, and then A has a perpendicular to this. Like you just take a perpendicular from this point from A to this line from M, and you push it until it meets the circumcircle. And this is supposed to be the orthocenter, right? That's sort of, actually in this case, it's supposed to meet it at this point here. Because there's two ways to look at this. One is you take a perpendicular from P and Q, intersect it, and that's sort of symmetric. Like you're looking at symmetric stuff. At the beginning, at least, you're looking at symmetric stuff in geometry because you can deal with them. If you figure out something for one thing, you can figure out the same thing for the other thing. And the other thing is, like, let's look at it with regards to A, and what does this thing mean for A? If I take any line here at a 90-degree angle and I intersect this with the circumcircle, then it's an orthocenter, right? What does that really mean is my question. So if this is 90, what do I have? I have, this is a triangle PQ. Draw it like this, PQ, and call this, let's not call it H, let's call it not R, PQ, M, and N. Let's call that right now. And let's sort of look at a problem backwards, what it is we need to prove. Let's call this perpendicular A0, this being A1 right here. So I know that A0, A1, M are concyclic, because this is 90, this is 90. This is why I'm introducing this point. I don't know if it's useful. And it's also concyclic with R, right? AR, ARM is MA1A. So this is also, R is also concyclic with these points. And then we have A0. And now, because this is the orthocenter, we have sort of we have a distance from A. We have a distance from A to N. We'll have that AA0 times AN is going to be something that's fixed. It's like if a triangle, actually this is a bad drawing, it's more like this. It's APQ, and you have a 90-degree angle, and the orthocenter, you have this times this is equal, say, this times this. But P is also the orthocenter of this triangle, so it's this times this. Is there any use to any of those points? Right now, currently, we don't know. We don't know what is useful and what isn't useful. You know, this is N, P, Q. So here's where I invite you to pause for, say, next 10, 15 minutes and see what would you do here? How would you connect these things? How would you push the problem further? And here's the next step. Okay, so now let's look at more what we have here. We have these powers of points. These lie on the same circle. One question is, how do we talk about N? On one hand, this is something that's like interesting that we could look at, which is that A0N times A0A is A0P times A0Q, right? And this is a power of point here. This is a power that we have from the, what's it called? From any triangle with the orthocenter. which means if I intersect this here, if I reflect n over here, say n prime, I'll have that this is on the, what's it called? It's on this circle. It's on this circle with diameter AH. And the reason I'm interested in this point is because then the problem becomes sort of, we need to figure out what this point is, but it's like, instead of the orthocenter, which seems a bit more distant, to me, I'm thinking this reflection of n with respect to this line PQ is more closer, much more closer to home. And now that's potentially an interesting thing to look at. Is there anything with this point right now? Because this is a perpendicular here. And we also know that this angle right here is 90 for this point. So if this is 90, right, this here is 90 because it's the diameter AH, that means this is parallel to this. So it's like we're reflecting everything here. This line, if I reflect it here, what am I getting? And it's reminding me a bit about, yeah, I'm reflecting actually everything on this line. It's like I'm reflecting it here. Maybe there's something there, maybe there's not. Right, but I have this sort of parallel condition now. It seems like that's maybe easier to prove. I don't know. Maybe we need to look at other things as well. So let's see what else is in this problem. So we have, what would happen if this was actually, if all of this was actually 90, right? If this was on the circumcircle, what would hold true for n? This is another way of thinking about the problem. Okay, well I have NP is perpendicular to AQ, but AQ is also perpendicular to HQ. So I would have HQ perpendicular to AQ, and NP perpendicular, so I'd have HQ is parallel to NP. And then also I need to have, like by pure symmetry, P and Q are sort of symmetric here, right? There's nothing, like I can relabel them and actually really get the same thing. And N is also symmetric with respect to them. So I'd have that HQ and HP is also parallel to NQ, i.e. I'd get this whole thing, H and Q is a parallelogram. So now that's actually, that's an interesting extra thing. That's saying here, if I reflect H with respect to P and Q, I'm going to get a point on the circumcircle. That's potentially a different way to look at this problem and try to solve it. And between these two ways, I invite you to pick which one is more attractive for you and try to solve it for the next 20 minutes. And here's the first step I'm going to do. I'm first going to look at this sort of reflection. Let's like analyze this a bit more. So let me clear up the problem board here. So I have now this picture and I'm looking at, okay, once I reflect H with respect to the midpoint of PQ, I should get a point here. And here's what's interesting to me now. Like that's really what the problem is. Reflect H with respect to the midpoint here and get a point on the circumcircle. What's interesting to me here is when I reflect H with respect to M, I'm also getting a point on the circumcircle. When I reflect H with respect to this midpoint, I should be getting a point on the circumcircle, right? What is special about me reflecting H with respect to these 2 points? And also when I reflect H with respect to this point, I'm now getting a point on the circumcircle. This is like background knowledge, knowing lemmas. And now when I reflect H also with respect to the midpoint of AH, I'm getting a point on the circumcircle. Do you see where I'm going with this now? This for me is now the end of the problem. Because really what I'm doing is I'm reflecting H with respect to the circle width A1, M, the midpoint of PQ, the midpoint of AH. all of these points lie on the circle with diameter M. Call this point X, where MX is 90. And why is this true? Why is this the case that they all lie on this, what's it called, circle with X, and call this midpoint PQRT, say. Why? Now, why is this here 90? Well, this thing is 90 because the center of this circle is, what's it called, X. So X perpendicular to PQ, X, connect X to the midpoint of the chord PQ, and you have a sort of XP is XQ, so we're done. So that's why this is 90. And now what am I doing? I'm saying H reflected with respect to X gives me a point on the circumcircle. Reflected with respect to this and this all give me points on the circumcircle. So let me call this point H prime. Actually, no, this is H prime. Let's call this H2 because I'm not creative with names. So we have H prime H2, A is 90. And now when I reflect H with respect to Y, the midpoint of PQ, I'll have H prime N is parallel to MY, and AN is going to be parallel to XY, because these are all reflections along the midpoint. And so this angle right here is going to be 90, and in other words, N is on the circumcircle around ABC. Now, this is one way to solve the problem, and another way to write it down is actually, it's called a homotety with center H and diameter 2. It takes the 9-point circle to the circumcircle. And when you think about it like that, that's what makes this problem like absolutely amazing. So this is one solution. Another way to go about if we were going to go with this idea is to say, so what we have here is that, and this is, mind you, difficult and more messy, but we're having that. So really what we need to prove is that this N, once reflected over here, is on the circumcircle. And now we see that we have a lot of circle here interactions. We have 1, 2, 3 circles that are interacting with one another, and they all pass through A and R. And when you have this situation where all these circles are passing through A and R, you're going to have a difficulty is one thing, trying to figure out what's happening where, but also you're going to have a lot of angles which are identical. And here this angle chasing gives us, we have this shared angle, for example, with N prime. We're going to have similar triangles. On one hand, we're going to have this angle, RA1A. We're going to have this angle is equal to RMA, and it's equal to RA0A. Connecting it to this point, which is on both this circle, that's 90, and that's this like perpendicular. We're connecting it to this line, right? Because this is the line where the orthocenter is connected to A. And now we have this angle, and we also have this shared here, RN prime A. So we have this angle here, RA1A is equal to RA0A. But also we have this angle here, Rn prime A. This thing here is equal to 180 minus RHA, which is equal to the angle RHA1. And now what do we have? We have RNA, we have this angle is equal to this one right here, and RA1H is equal to RA0A. In other words, we are going to have the angles R and prime A0 is going to equal to the angle RHA1. We're going to have the angle RA0 and prime. Actually, RA0 and prime is equal to the angle. So RA0 and prime is going to be equal to RA1A. RA1H is what we care about. And now we have a similarity between these two triangles. Now, why is this similarity interesting? Well, when we are really taking a point here and we're reflecting it to get n, we want to prove that this angle here is an angle that RA has with the triangle on the chord of the circumcircle of ABC. And we want to prove that that is the same angle as this one here, in other words. But the reason that is the case, like we care about this angle, we know that we have this side, we know the length of this, we know this, and we have an angle here. And that is how we really finish up. We finish up now, we know that the triangles, say Rn prime A0 is similar to the triangle RHA1. And from this similarity, we get that this n prime A0 over, so n prime A0, which is here, over HA1 is going to equal to RA0, or you can have RA0 over RA1. And now what happens when we reflect? Well, when we reflect, we're going to have the points here because H is reflected over here, and we are going to have, so let's first do n prime A0. N prime A0 is equal to NA0. And then here we're going to have HA1 is going to equal H2A1. Like we know this is our similarity. And then this is going to be equal to RA0 over RA1. And I'll take that into account and the fact that this shared angle, that this is a shared angle, that the angle RA0, RA1H2, RA1H2 is equal to the angle RA0 and N. RA0N. Now combine this with this thing right here, and then you have side angle side similarity, which gives you that this angle is equal to this angle. Now, this seems very difficult. This solution seems a lot more natural or intuitive than this one for some people. And I think the reason that might happen is because you don't have a lot of experience with this intersection of these two circles. This point right here, when you have an intersection with two circles, circle 1 and circle 2, and you take like these two, you take two lines through one of the intersections. Call this A, B, C, D, E. And if you take this point R, then you have this triangle is similar to this triangle. And also, I think you have another triangle, I think. RD, RBD, and RCE are similar as well. And this sort of similarity thing is used very often in problems, because from there you can get to a lot of interesting things that you can use later on in the problems. This is called spiral similarity, I think. And it's a cool thing. And that's like sort of a lemma, a background thing you can have, and why you would attempt to do anything like here. This looks like a horrible picture, but the main issue is you're trying to like just focus on A0, really get rid of P and Q. Like right here, you don't care about P and Q at all. And try and see, okay, what do I have for this point here once I intersect this with this circle? I've gotten rid of P and Q. I have my own sort of definition of N, of the orthocenter. What do I need to prove? And then you see, okay, I need to prove this. What do I know about this configuration that I have? I have a perpendicular from A to a line through M. Okay, that's just a point on this circle. Circles usually better than just like a perpendicular line through something. like something just like a line, any sort of variable line in a perpendicular. A circle is nicer, it has more structure. And when you take into the fact that also this point lies on that circle as well, it makes the circle nicer. And also this midpoint, like there's more points which are known to you, which lie on this circle. So that is why you want to call it like that. You call this point because it lies on another circle, which is nice. And now what you're really trying to do is connect these two circle intersections with something that you know. And that is how you motivate this sort of solution. This finishes up our problem, and as always, thanks for problem solving.